Lesson's going to be about volume of surfaces that are created when you revolve a curve around a vertical or horizontal line. And today we're going to focus on horizontal line. And we're going to use either disk or washer methods. So first thing we need to define is what a cross section is. So a cross section is the intersection of a solid with some sort of plane. And A of x is the area of that cross section in the plane, perpendicular to, in this case, we're going to be perpendicular to the x-axis, passing through the point x. They could be perpendicular to the y-axis when we revolve around either the y-axis or a vertical line. But basically what happens is you have something that sort of looks like this sort of shape. And we're going to divide that solid into slabs, or a lot of times today is going to be circles or discs of equal width. And we're going to take the area of these and multiply them by the width of the slabs. And the volume is going to equal the summation of all of those slabs areas. The more slabs we create, the better our approximation is, and that sounds exactly like Riemann sum, because it really pretty much is. And so basically, what we're going to be doing is that the volume, we're going to say if S is the solid that lies between x equals a and x equals b, the cross-sectional area of S in a plane through x and perpendicular to the x-axis is a of x, where a is a continuous function, then the volume is the summation, and the limit is n approaches infinity, of this n rectangles, their area times the change in x, or the width of the rectangle, which is basically an integral. Okay, so we're having a to b of the area of them times dx. So let's take this with revolutions. So find the volume of the solid that is formed when f of x equals the square root of x on the interval from 0 to 4. So we are looking at from here to here, and we're going to rotate it around the x-axis. So even though my graph is only to there, I'm going to have something that's going to kind of look like this. And it's been revolved, so these are all going to kind of be like this. As I've spun them around, and I'm doing as best as I can to draw it. But think about what we saw when we looked at the calculus of motion in class the other day. We saw it create those circles or those discs. Okay, and here I have a bunch of circles basically. And the radius of each of these circles is this height of the function. Okay, you see that? That's the radius. So my radius here is the square root of x. Same here, same here, same on every single one. So I drew 4 of the discs in, but imagine if I put infinitely many discs in between the whole thing. So we're looking at the integral. And so the area here, instead of a of x is not just square root of x, because square root of x is my radius of that circle. The area of a circle is pi r squared. So a of x is going to be pi square root of x squared, or just pi x. Okay? It makes our integral a little bit easier. So we're going to have 0 to 4, because that's where we're starting. Our smallest circle is all the way over here. Again, I have infinitely many circles throughout this entire thing. Okay? From 0 to 4, we want to do as many circles as possible of that area function and dx. Don't forget your dx, because we need to know what we're taking our integral with respect to. I can pull the pi out on the outside because it's a constant. And then I'm going to have 1/2 here, divided from 4 to 0, which is going to be pi times 1/2 4 squared minus 0. So I'm going to get 8 pi. That's what my volume is equal to. So again, this was an example of a disk because each shape that it created when I revolved around the x-axis was circles. Let's try another example. So here I find the region R enclosed by the curves y equals x and y equals x squared, and then it is rotated around the x-axis. Find the volume of the resulting solid. So first thing I want to do is draw those two shapes. I've got a line and I have a parabola. And you can see that I've got these boundaries. It didn't tell me, like the last problem, from 0 to 4, but I can see the natural boundaries that we're looking at. We're looking at here and here. So we're going to be looking at from 0 to 1. Now I'm going to kind of try to sketch this. So that's that outside. So this is almost like a cone that has this other shape cut out of it. So then we spin it around. Actually, I should use another color. So then like here, you have this outside one and inside one. Okay, so you can see, I'll do another one over here, how now I have a washer, okay, or almost like, it's called an annulus, or almost like a flat donut. You have a circle within another circle. So my A of x is going to be, I want the outer circle minus the inner circle. So when we're doing this, we're going to have the integral from 0 to 1. I need to figure out which one has the longer radius. That's going to be, in this example right now, from the x-axis to just x is the outer one, and then the inner one is x squared. Okay? So we'll have pi x squared minus pi x squared squared. Okay? So then in my integral, I'm going to have pi x squared minus pi x to the 4th dx. Don't forget that dummy variable. I can pull the pi out of both of them again. It's a pretty common thing to do on these. And then I'm going to do the integral. Pi times all of that. So we'll have 1/3 minus 1/5. Pi times both. 5/15 minus 3/15 is 2 pi over 15. That's what my volume is equal to. Okay. So again, we've spun it around the x-axis, so we're taking our integrals with respect to x. And on this, because it was a washer, I had to do the larger radius minus the shorter radius in my pi r, large R squared minus pi small r squared. One more problem, and it's actually the same equations. So find the region of the solid obtained by rotating about the line y equals 2 instead. So instead of rotating it, so our axis of rotation on the last problems have been along the x-axis. We're now going to move that higher. So instead of spinning it around there, oops, we're going to spin it like somewhere up here. Okay. This is going to make it harder. It's going to look more like that. That outside piece. Still gonna have washers. Okay. But my actual radii have changed. Now, do this is my inside radii. And this is my outside radii. Okay. Now, when I do this outside radius, okay, it's like 2 minus this small little amount of x squared. Because the height here is x squared, and this was all the way up at 2. And then my little radius is 2 minus x. Okay? Because we're measuring from 2, but we want to remove this little height of x from it. So now this integral is going to be a little bit harder. dx. We're still doing the same bounds of integration from 0 to 1. Okay. Oops, missed the square on that one. Double check whenever you're doing this that you always have your radius squared, because the area of a circle, which is all we're doing here, always has pi r squared. So I'm going to pull the pi's out on the outside again. Now, once I have these, you could be a little intimidated by these integrals. But when we're looking at it, rather than be intimidated and worry about any u subs, what we could actually do would be to actually just FOIL out those two binomials. So when we FOIL out those two binomials, 0 to 1, we have 4 minus 4x squared plus 4th minus 4 plus 4x minus x squared all dx. And we'll combine our like terms. And then do our integral. Sometimes on the AP exam, it'll say set up but do not evaluate, because depending on the actual equations, these can get messy. Luckily, we're only evaluating at 1 and 0, so it's not too terrible. Which ends up as 8 pi over 15. And that concludes today's lesson.